Hello and welcome to my YouTube channel. Today I shall be treating the topic complex numbers. Please hit on the subscribe button below if you've not done so already. Thank you. Consider the following quadratic equation: x squared plus 1 equal to 0. If we attempt to solve this, we have x squared equal to minus 1. We now take square root on both sides and we have x equal to plus or minus the square root of minus 1. Now at this point, if we attempt to use our calculator in normal mode to evaluate the square root of minus 1, it displays an error. Now this means that the square root of minus 1 is not a real number. It's not a real number. And of course, you know what real numbers are. Whatever number comes to your head right now is a real number. Be it 2, 4, 6, 3.5, 1 over 2, whatever comes to your mind right now is a real number. For example, the square root of 4 is 2, a real number. The square root of, say, 16 is 4, a real number. The square root of 10 is a real number. Square root of whatever comes to your mind, the square root is a real number. So what happened here? The reason, we couldn't have a real number for the square root of minus 1 is actually because of the presence of this negative sign under the square root. So going forward, whenever we have a negative sign under our square root, we know that the result will never be a real number. So in normal mode, it will always display the error message. So in order not to let this equation go unsolved, mathematicians now agree that let the square root of minus 1 be what? Be letter I. So that if the square root of minus 1 is I, then this equation will have a solution. So it would mean that x is equal to plus or minus what? I. That is to say that the square root of minus 1 is equal to what? I. And so if this is true, then I squared is equal to minus 1. Root minus 1 is I, and if you square both sides, I squared is equal to what? Minus 1. These are two important results, we shall be using going forward. So if x is equal to plus or minus I, does this make sense? Does this qualify to be called a solution to this equation? Let us see if it is. So we have x squared plus 1 equal to 0. Now we have said that the square root of minus 1 is I. So the solution to the equation is x equal to plus or minus I. So let us take I, plus I for example, to check. So if we substitute I into the left-hand side of the equation, what do we have? We get I all squared plus 1. Now we have said that I is equal to the square root of minus 1, which means that I squared is equal to minus 1. So I squared is minus 1 plus 1. So minus 1 plus 1 is equal to 0, which is what we have on the right hand side. What do we observe here? We observe that with the value x equal to I, the equation is satisfied. Therefore, x equal to I qualifies to be a solution, to the given quadratic equation. The same thing happens if you substitute x equal to minus I into the equation. You get minus I all squared plus 1. Of course, there's minus here, so the square of a minus sign is a positive sign. So that becomes I squared plus 1, which is equal to minus 1 plus 1, which again is 0. So that x equal to minus I also satisfies, the given quadratic equation. Therefore, we conclude at this point that the square root of minus 1 is equal to I, and the square of I is equal to minus 1. With this result, we will be able to evaluate the square root of any negative number. I shall show you with a few examples. Now we can evaluate the square root of minus 64. Let us see. Once again, if you use your calculator in normal mode, to evaluate this, you have the error message once again. The reason is because of the negative sign under the square root. So how now do we go about this? Using the new information we now have. From our sword, we can write this as the square root of minus 1 times 64. Since minus 1 times 64 is the same thing as minus 64, so we're in order. We can now split this using the rules of sorts as square root of minus 1 times the square root of 64. Now what is this? Square root of minus 1, and this is now familiar. What is this? Nothing but what? I. We have said already that the square root of minus 1 is I. So we can now replace I, for this, and that becomes I times root what? 64. And of course, root 64 is what? Is 8. So that becomes I times 8. And I times 8 is nothing but what? 8I. So the square root of minus 64 is nothing but what? 8I. Another one is the square root of minus 16. So again, we can write this as the square root of minus 1 times 16. Using our sort rules, we can separate this as the square root of minus 1 times the square root of 16. And from what we know already, the square root of minus 1 is nothing but what? I times the square root of 16 is 4. So that I times 4 is 4I. So the square root of minus 16 is 4I. Another example is the square root of minus 8. We can write this as the square root of minus 1 times 8. So this becomes the square root of minus 1 times the square root of 8. The square root of minus 1 is what? Is I. This is equal to I times, we can now split 8 as what? 2 times 4. So this becomes I times the square root of 2 times the square root of 4. So this becomes I times the square root of 2, and of course the square root of 4 is nothing but what? 2. So that I times root 2 times 2 is nothing but what? 2I root 2. So once again, the square root of minus 8 is equal to 2I root 2. So we should bear in mind that wherever we see I, we should know that I is equal to what? The square root of minus 1. And I squared is equal to minus 1. One last example. Square root of minus 1 over 4. So we can write this from indices or from sorts as the square root of minus 1 divided by the square root of 4. Again, square root of minus 1 is nothing but what? I over the square root of 4 is 2. So the square root of negative 1 over 4 is equal to I over 2, where our I in all cases is always what? The square root of minus 1, and I squared is equal to what? Minus 1. Now let us define what a complex number is. Definition. A complex number is a number that can be expressed in the form a plus ib, with a and b here being real numbers and b is not equal to 0. A is called the real part of the complex number and b is called the imaginary part of the complex number. So what does this definition mean? This is what it means. So we're saying that if we see a number written in the form a plus ib or a plus bi, this number is called a complex number. What gives you the idea that it's a complex number is the presence of our I. Remember this little man I? Yes. Now this complex number comprises of two parts. The first part is a, and that a is called the real part of the complex number, and this b is called the imaginary part of the complex number. But the fact here is this: a and b are both real numbers. But what makes b the imaginary part is the fact that it is, it stands, with our little man I. So b is the imaginary part of this complex number, while a is the real part of the complex number, a plus bi or a plus ib. Now we say that b is not equal to 0. Why? Because imagine that b is 0 here. What this becomes is a plus 0, which is equal to what? A. And if you see that if b is equal to 0, then our I is gone. And once I is lost, the number you now have is a real number and no longer a complex number. So what makes the number complex in the first instance is the presence of our little man I. So a complex number is a number that has, an I, on it. So we have the real part and we have the imaginary part of the complex number. So when we bring together all complex numbers, they also form a set, just like we have the set of real numbers R. Now the set of all complex numbers is denoted in mathematics with the letter C. So while R denotes the set of all real numbers, capital letter C denotes the set of all complex numbers. So all these numbers, having real and imaginary part, fall under, the set C, set of all complex numbers. Now, every complex number can be represented by a single symbol, and that symbol is letter Z. So going forward, we shall be using letter Z to denote what? A complex number. So if I say a complex number Z equal to whatever it is, so I'm using Z to denote a complex number. So we are now saying that I can now write Z equal to A plus IB, being the complex number A plus IB. So Z is a complex number, A plus IB, where A is the real part of the complex number, which I'm going to write as real part of complex number Z is equal to what? Equal to A, and imaginary part IMZ of the complex number Z equal to what? B. So these are the notations we shall be making use of going forward. So Z is a complex number, A plus IB, and you now know why it is called a complex number. This complex number has two parts, the real and imaginary part. So the real part of the complex number Z, which we denote as REZ, is equal to A, and the imaginary part of the complex number Z is denoted as IMZ equal to what? B. Now the following are examples of complex numbers. 1. Z equal to 6 plus 2I. So here, the real part of this complex number Z would be what? You can guess is 6, the part without the I. While IMZ, the imaginary part of the complex number Z, is equal to what? Equal to 2. This, the number that has an I by it. So Z equal to 6 plus 2I is a complex number with real part Z and imaginary part what? 2. Another complex number, say Z2 if you want, equal to, say, minus 4I plus 2. Again, it's a complex number because I've seen I already. So this is a complex number with real part of Z2 is what? Is 2, the part without the I. And the imaginary part of Z2 is equal to what? Negative what? 4. The number standing, with the letter I. And finally, Z3 equal to 7I. Yes, this is also a complex number. How? Let's see. So we want to find out the real part of Z3 and of course the imaginary part of Z3. So let's take a look. Now, Z3 is equal to 7I, which means that one of the parts is missing, the real part, because we said A plus IB. A plus IB, where A is the real part and B is the imaginary part. But on this complex number, 7I, the real part is missing. So the real part there is what? Is 0. And the imaginary part is what? 7. So what do you see? So you see that for a number to be a complex number, it is possible for the real part to be 0, but it is never possible for our definition for the imaginary part to be 0. Once the imaginary part of the complex number of a number is 0, that number fails to be a complex number. It only becomes a real number. We shall now learn how to evaluate certain powers of our little man I. We know two things already. We know that I is equal to the square root of minus 1. And again, we know that from here, if we square both sides, then I squared is equal to what? The square root of minus 1 squared, which is equal to what? Minus 1. So I is equal to the square root of minus 1, and I squared is equal to what? Minus 1. We shall use these two information, to evaluate certain powers of I. Number 1, we want to evaluate I raised to the power 9. Now the way we go about this is this. We are going to express, this power of I in terms of I and I raised to the power 2 only. Of course, there are other ways of doing it, but I find this method to be a little bit, easier for us. This is what we're going to do. I just come over here, I divide 9 by 2. So 9 divide 2. And I will divide by 2, at all times. So 9 divided by 2 is nothing but what? This is what? 4. Remember what? Remember 1. So this means that I can write 9 as 2 times 4, remainder 1. I'm now going to use this idea, over here. So what do I write here? I'm now going to write this as I squared, the 2 here, then outside I'm going to put 4. Remember what? Remember 1. So remember I raised to the power 1, but I'm not going to write 1 there. So there's a 1 up here. So what is this? By indices, 2 times 4 is 8. And there's 1 here, so that 8 plus 1 is 9. So what we have on the left-hand side is exactly, the same as what we have now on the right-hand side. But what I've done here is, I've expressed this power 9, I raised to the power 9 in terms of I square and I raised to the power 1 only. How does this now make sense to us? Let us see. From here, I can write, I know what I square is. What is I square? I square is minus 1. So this is minus 1 raised to the power what? 4 times I. So minus 1 raised to the power 4 is what? Is 1. Remember, whenever you raise a negative number to the power of an even number, the answer is always 1. And of course, if the power here is odd, then this will always be minus 1. So this becomes I raised to the power 1 minus 1 raised to the power 4 is 1 times I. So 1 times I is nothing but what? I. If you like, you know I is equal to what? The square root of minus 1, but it makes sense just to leave it like as I. So I raised to the power 9 is equal to the same thing as I. The second example. Let's evaluate I raised to the power 15. So go back to our little trick. I said we always divide by 2. So 15 divided by 2 is equal to 7, remainder 1. So we can write 15 as 2 times 7, remainder 1. Using this idea, I can now write this as I squared. The 2 will always come inside. What will be outside? 7 times what? What is left? I raised to the power 1, which is I. So with this, I'm okay. I can now write, what do I know? I know that I square is minus 1. So this is equal to minus 1 raised to the power 7 times I. Like I just explained, seconds ago, whenever the power of a negative number is odd, that number remains what? Negative. So minus 1 raised to the power 7 remains minus 1 times I. So that minus 1 times I is equal to minus I. Therefore, I raised to the power 15 is equal to minus I. So let us take one more. So here we have I raised to the power 2000 plus I raised to the power what? 24. It would have been anything, no problem. So let us go back to our little trick and see how to break this down. So the first one, 2000. We divide always. 2000 divided by 2. That gives us 1000, remainder 0. So I can write 2000 as what? 2 times 1000, remainder what? 0. That's okay. Then go back to the second one. We have 24 divided 2. That gives us what? 12. Remainder 0. So that 24 can be written as 2 times 12. Remainder 0. And I'll go back to what I have. I can now write this as, this is I raised to the power 2. And what will be outside? 1000. 1000. Remember what? 0. So times nothing. Because that's it. Then plus the second one is I raised to the power 2 again. Remember 2 is always inside. What will be outside? 12. Remember 0. So remember nothing. So there's nothing to add up again. So 2 times 1000 is 2000. And then 2 times 12 is 24. We know already that our I squared is what? Is minus 1. So I squared is minus 1 raised to the power 1000 plus our I squared again is minus 1 raised to the power 12. Now I had said already that 1000 is an even number. So minus 1 raised to the power 1000 is 1. Plus 12 again is an even number. So minus 1 raised to the power 12 is 1. So that 1 plus 1 is equal to 2. So this is how, we go about evaluating the powers, the different powers of I, no matter what, they are. So just try your hands quickly on I raised to the power 1, 2, 3 and see if you can get it. Equality of complex numbers. So we want to now know when two complex numbers are said to be equal. So given two complex numbers, say Z1 equal to A plus BI and Z2 equal to say X plus YI. So Z1 will be equal to Z2. So the complex number Z1 will be equal to the complex number Z2 if and only if their real parts are equal and the imaginary parts also are equal. What are we saying here? Now, what's the real part of Z1? We know already by now that the real part of Z1 is A. And the real part of Z2, is what? Is X. Now the imaginary part of Z1 is B. And the imaginary part of Z2 is what? Is Y. So these two complex numbers, z1 and z2, will only be equal if and only if a is equal to x and b is equal to y. So the two complex numbers are equal if their real parts are equal. The real parts a and x are equal, and the imaginary part b and y are equal. So if I have, for example, a complex number z1 equal to 3 plus 6i, and I have another complex number z2 equal to 6i plus 3, then these two complex numbers are the same, or are equal. That's the word, are equal, because the real part of z1 here, the real part of z1 is what? Is 3. And the real part of z2 is also 3. The imaginary part of z1 is 6. And the imaginary part of complex number z2 is also 6. So what do you see? They have, the same real numbers. They have the same real parts, and they also have the same what? Imaginary parts. Since the imaginary part and the real parts are the same, we can now write that z1, complex number z1, is equal to complex number what? Z2. Now we use this idea, to solve certain problems that involves equality, and I'll show you with an example. Example: if a plus ib is equal to minus 6 plus 8i, find the values of a and b. Now, from this example, it's obvious from the statement that the complex numbers are equal. How do you know? There's an equality sign between them. We are told that the complex number a plus ib is equal to the complex number minus 6 plus 8i. And we're asked to find the values of the unknowns, a and b. Since we have seen clearly with our eyes that the complex numbers involved are equal complex numbers, what do we know about equal complex numbers? We know that if complex numbers are equal, then their real parts must be the same, as well as their what? Imaginary parts. So the real part of the complex number on the left hand side is a, and since they are equal, it must be equal to the real part of the complex number on the right hand side, which is what? Negative 6. So a, the real part on the left hand, is equal to the real part minus 6 on the right hand side. Equally, the imaginary part on the left hand side is b, and it must be equal to the imaginary part on the right hand side, which is equal to what? 8. Therefore, a is equal to negative 6 and b is equal to 8. We have used the concept of what? Equality of complex numbers to get this sorted out. We'll now take a slightly, more interesting example. Example: if z1 is equal to 2x plus 4 plus y plus 8i is equal to z2, and z2 is equal to 4x minus 6 plus 4 minus yi. Question is, find the values of x and y. So once again here, the statement is clear and obvious that there are two complex numbers. The first complex number is z1, and z1 has real parts 2x plus 4, because these are the numbers without I, and the imaginary part here is y plus 8. While z2 has real part 4x minus 6, and the imaginary part is 4 minus y. Now we are told from the statement here, we can see from the statement rather, that z1 is equal to z2, and we're asked to find the values of x and y. Now what do we know? We know that if z1, complex number z1 and z2 are equal, then what happens? The real part of z1 must be equal to the real part of z2, and the imaginary part of z1 must be the same as the imaginary part of what? Of z2. So we are saying that since z1 is equal to z2, then what will happen? They will have the same real parts and the same what? Imaginary parts. So the real part of z1, 2x plus 4, will be the same as the real part of z2, which is what? 4x minus 6. And what we have is a linear equation in x, which you can solve. So if we take like terms, we're going to have 2x is plus 4 to the left becomes minus 4x equal to, this is minus 6 plus 4 to the right becomes minus 4. So 2x minus 4x is negative 2x equal to negative what? 10. If we divide both sides by minus 2, we have that x is equal to 5. So the value of x is 5. We now proceed also to find the value of y. What we have done here is the fact that since z1 and z2 are equal, then the real parts are equal. Also, since z1 and z2 are equal, they must also have equal imaginary part. That is to say, the imaginary part of z1, which is what? Y plus 8, must be the same as the imaginary part of complex number z2, which is what? 4 minus y. Again, we have a linear equation in y, which we shall solve. So this is y, this is minus y to the left, plus y equal to 4. This plus 8 to the right becomes negative 8. So y plus y is 2y equal to 4 minus 8 is negative 4. So if we divide both sides again by 2, we have that y is equal to negative 2. Therefore, x is equal to 5 and y is equal to negative 2. Now, with this, we can now know what our complex numbers really are. Let us see. We are told that z1 is equal to 2x plus 4 plus y plus 8i. So now x is 5 and y is minus 2. So let's put them both here and see what z1 really is. So z1 is nothing but 2, x is 5, so 2 times 5 plus 4 plus y is minus 2, so minus 2 plus 8i. So z1 is equal to 2 times 5 is 10 plus 4 plus minus 2 plus 8 is 6i. So 10 plus 4 is 14. Therefore, z1 is 14 plus 6i. So the complex number z1 we're talking about here is nothing but what? 14 plus 6i. So let us see what z2 is. So z2 we are told here is what? 4x minus 6 plus 4 minus yi. So z2 is 4, our x again is 5 minus 6 plus 4 minus y is minus 2, so that's minus 2, that is 4 plus 2i. So that 4 times 5 is 20 minus 6 plus 4 plus 2 is 6, so 6i. So that z2 is equal to 20 minus 6 is 14 plus 6i. What do you observe? We observe that indeed z1 is equal to z2. So our solutions for x and y are indeed correct. So you have seen here how we use the concept of equality of two complex numbers to solve certain problems. Sometimes it leads us to quadratic equations, other times to simultaneous equations, and other times to linear equations, anything. But just take note here that whenever two complex numbers are equal, they must have equal real parts as well as equal imaginary parts. Addition and subtraction of complex numbers. Now, just like we add up real numbers and subtract real numbers, we do the same to complex numbers. However, in the case of complex numbers, we have to take note of the following. Now, when adding or subtracting two complex numbers, we do this component wise. That is to say that you only add real parts together and imaginary parts also together, as well as subtraction. So let's take an example to clarify what we are really saying. If we have two complex numbers, z1 for example equal to 6 plus 7i, we have another complex number z2 equal to 4 minus 3i. So we want to find z1 plus z2. That's the first thing. So we want to add up. So what is z1? z1 is 6 plus 7i plus what is z2? z2 is 4 minus 3i. So how do we now add? You observe that on the first complex number, the real part is 6 and the imaginary part is 7. And in the second complex number, the real part is 4 and the imaginary part is negative 3. So while adding, we only add real parts and imaginary parts. So the real part here, the first one is 6. So 6, we add it to 4, the real part of the second complex number. Of course, plus the imaginary part of the first complex number is 7. And the imaginary part of the second one is minus 3i. That is it. We add component wise. So this gives us 6 plus 4 is 10 plus 7 minus 3 is 4i. So z1 plus z2 is equal to 10 plus 4i. If we wish to subtract, so z1 minus z2, that would now be z1 is 6 plus 7i minus z2 is 4 minus 3i. Of course, we have a bracket, so we must clear our brackets first. So we have 6 plus 7i minus times 4 is minus 4, and then minus times minus 3i is plus 3i. So once again, we go component wise. Real part here is 6, the real part here is minus 4. So 6 minus 4 is 2. The imaginary part on the first complex, the imaginary part here is 7 and 3. So 7 plus 3 is 10i. So z1 minus z2 is equal to 2 plus 10i. So you see here that if you have two complex numbers and you add up, what you have, remains a complex number. And if you subtract two complex numbers, in whatever order, the result you're going to have remains also what? A complex number. Multiplication of complex numbers. Now, we carry out, multiplication of complex numbers just, in the same manner as that of real numbers, except that here we should always bear in mind that our I is equal to the square root of minus 1 and our I square is equal to what? Minus 1. So let us take one or two examples, to illustrate what we are saying. Number 1, we want to multiply 4 minus 5i times 3 plus 2i. So it's a normal, multiplication process, except that now we are dealing with complex numbers. So the first complex number here is 4 minus 5i, with real part 4, imaginary part minus 5, and the second complex number is 3 plus what? 2i. So we carry out our normal, expansion. So we use 4 here, the first term here, and multiply everything, 3 plus 2i. Use the second term, minus 5i, to multiply everything here, 3 plus 2i. So now do it carefully. So 4 times 3 is 12, and then 4 times 2i is plus 8i. Minus 5i times 3 is minus 15i, and then minus 5i times 2i is minus or negative 10i squared. So we continue to break it down. So this is 12. 8i minus 15i is negative 7i minus 10 into, now recall, that our I is equal to the square root of minus 1, and our I squared is equal to what? Minus 1. So I've seen I squared here. So I squared is nothing but what? Negative 1. So with this in mind, this becomes 12 minus 7i, so that minus 10 times minus 1 is plus 10. And this gives us, we have 2 real parts and 1 imaginary part. We add up. So 12 plus 10 is 22 minus 7i. So what do we observe? That we have two complex numbers which we multiplied, and the result also is a complex number. Example number 2. To multiply 3 plus the square root of minus 64 and the square root of minus 16 minus 2. If you look at this, quickly, it doesn't look like complex numbers, but they are, because by now that the square root of a negative number will always give us I, right? Something that has I in it. And once there's an I involved in a number, the number becomes a complex number. So if you have that at the back of your mind, you should know that what you're dealing with is still a complex number. So with that, we can rewrite this, in terms of i's. How? So this means 3 plus. Now you know already that I can write this as minus 1 times 64. We can write this one as minus 1 times 16 minus 2. This becomes 3 plus, we can split it up as minus 1 times, now this times the square root of 64. We can split this one up also as the square root of minus 1 times the square root of 16 minus 2. This becomes 3 plus the square root of minus 1 is I. So this is I times the square root of 64 is 8 into the square root of minus 1 again we know is I times the square root of 16 is 4 minus 2. This gives us 3 plus I times 8 is 8I into I times 4 is 4I minus 2. So we have seen clearly now that what we had was a complex number. It's now time to expand. So like we did before, we have 3 multiply everything here, 4i minus 2, then plus 8i multiply 4i minus 2. So 3 times 4i is 12i. Then 3 times minus 2 is minus 6. 8i times 4i is plus 32i squared. And finally, 8i times minus 2 is minus 16i. Recall again that I squared is equal to what? Negative 1. I squared is equal to minus 1. So this gives us 12, of course, I like it already. So 12i minus 16i is equal to minus 4. So this is minus 4i minus 6 plus 32 into I squared is minus 1. So instead of I squared, we'll now replace with minus 1. So that becomes minus 4i minus 6 minus 32. So plus 32 times 1 becomes minus what? 32. So that this becomes negative 4i minus 6 minus 32 is minus what? 38. And that is it. So that's the answer. So the real part here is minus 38 and the imaginary part here is minus 4. Division of complex numbers. Now, to understand this division of complex numbers, we are going to define what we mean first by the conjugate or the complex conjugate of a complex number. Definition. A complex conjugate of a complex number is another complex number that has the same real parts as the original complex number and the imaginary part has the same magnitude but opposite sign. And then remark, the product of a complex number and its conjugate is a real number. So let me explain this with an example. For instance, we have a complex number z equal, say, 2 plus 3i. There's another complex number that relates with this, which we denote as z bar. So if z is a complex number, then z bar is called the complex conjugate. It's called the complex conjugate of the complex number z. Now the complex conjugate of the complex number z has the same real part as z, which is what? 2. It has the same imaginary part as z, which is what? 3. However, on the complex conjugate, the sign of the imaginary part is the opposite one. So z had plus, so z bar will have minus. So z is a complex number 2 plus 3i. Z bar is a complex number 2 minus 3i. And z bar is called the complex conjugate of the complex number z. And of course, z is also the complex conjugate of the complex number z bar. So a complex number and its conjugate are the same, except that on the conjugate of a complex number, the sign of the imaginary part, emphasis, the sign on the imaginary part, will be the opposite one. So that if the original complex number has a minus at the imaginary part, the conjugate will have a plus at the imaginary part. Now the remark says that the product of a complex number and its conjugate is a real number. Let us see. We are saying now that if we multiply this complex number z by its conjugate, we are saying that we're going to have a real number, and that's an interesting result. Let us see. So here we have 2 plus 3i, and then the conjugate is 2 minus 3i. So we multiply, let us see. This is 2 into 2 minus 3i plus 3i into 2 minus 3i. So 2 times 2 is 4. 2 times minus 3i is negative 6i. 3i times 2 is plus 6i. And 3i times minus 3i is negative 9i squared. So this is 4 minus 6i plus 6i is 0. And what we have left is negative 9i squared. Recall again that our I squared is equal to minus 1. So this becomes 4 minus 9 into minus 1 equal to 4. Minus 9 times minus 1 is plus 9. And 4 plus 9 is equal to 13. And what is 13? 13 is nothing but what? A real number. Why is it a real number? Because a number that has 0 as its imaginary part. So we had two complex numbers, a complex number and its conjugate. So we had z equal 2 plus 3i. Its complex conjugate is 2 minus what? 3i. We multiplied z and z bar, and we ended up with a number that is not a complex number. So we are saying here that the product of a complex number and its conjugate is always a real number. So I take one more example. Example 2. We have a complex number z equal minus 5i plus 2. So the real part of this complex number is 2 and the imaginary part is negative 5. So the complex conjugate of this complex number is z bar. So z bar means complex conjugate is equal to what? It will have the same real part as z, but the imaginary part will have the opposite sign. So the opposite sign here is plus, so it is 5i plus 2. So while minus 5i plus 2 is a complex number z, 5i plus 2 becomes the complex conjugate of complex number z. So once again, we say that if we multiply z and its complex conjugate, we should end up with a number which is not complex, rather real. Let us see. So z times z bar, that is minus 5i plus 2 times 5i plus 2. We expand. So this is minus 5i into 5i plus 2, then plus 2 into 5i plus 2. So minus 5i times 5i is minus 25i squared. Then minus 5i times 2 is minus 10i. 2 times 5i is plus 10i. And then 2 times 2 is what? Plus 4. Again, our I squared is minus 1. Remember, at all times. So this becomes minus 25 into minus 1. Minus 10i plus 10i is 0. But that means 10i minus 10i, 0. What is left there is plus 4. Minus 25 times minus 1 is 25 plus 4. 25 plus 4 is what? 29. And once again, 29 is not a complex number, rather what? A real number. We have shown now with a second example that the product of a complex number and its conjugate is always a real number. We shall now apply this concept of conjugate in our division of complex numbers. Example number 1. We're asked to divide 7 minus 4i by 4 plus 3i. And this is obviously division of two complex numbers. So the numerator is a complex number with real part 7, imaginary part minus 4. And the denominator is also a complex number with real part 4 and imaginary part plus 3. So we want to carry out this division and leave our answer in standard form. How we go about this is this. We are going to multiply the numerator of this fraction by the complex conjugate of the denominator and multiply the denominator of the same fraction by the complex conjugate of the denominator. Very simple. Let's see. This is equal to 7 minus 4i over 4 plus 3i. That's the fraction given to us. We now multiply the numerator by the complex conjugate of the denominator. So we have 4 plus 3i. What's the conjugate of 4 plus 3i? You know already. It's 4 minus 3i. So we multiply the numerator by 4 minus 3i and multiply the denominator also by 4 minus 3i. This is what we do when carrying out division of complex numbers. So if we tally this up, so this simply means 7 minus 4i times 4 minus 3i divided by 4 plus 3i times 4 minus 3i. So we now carry out this multiplication carefully till we get what we want. So 7 times 4 is, okay, let's just do it properly. 7 into 4 minus 3i, then minus 4i into 4 minus 3i, divide by 4 into 4 minus 3i, then plus 3i into 4 minus 3i. So this gives us 7 times 4 is 28. That's 28. 7 times minus 3i is minus 21i. Minus 4i times 4 is negative 16i. Then minus 4i times minus 3i is plus 12i squared. That's for the numerator. Divided by 4 times 4 is 16. 4 times minus 3i is minus 12i. 3i times 4 is plus 12i again. Then 3i squared times minus 3i squared is minus 9i squared. If we tally this up, we get 28. Minus 21i minus 16i is minus 37i plus 12. I've seen I square. So what is I square? I square is minus 1. So I square is minus 1. Divide by 16. Minus 12i plus 12i is 0. So what is left? Minus 9. Again, I've seen I square. I square is minus 1. So minus 1. So this gives us 28, minus 37i. So 12 times minus 1 is minus 12. Divide by 16. Minus 9 times minus 1 is plus 9. We'll now tidy it up, one more time. So this gives us 28 minus 12. Since these are both real, 28 minus 12 is 16 minus 37i. Divided by 16 plus 9 is 25. We're asked to leave the answer in standard form. Now, what is our standard form? If you recall, we said that the complex number z is written as what? A plus ib, or if you like, a plus bi. This is standard form, where we have the real part plus the imaginary part. So to write this one, the solution in the standard form, this is equal to 16 divided by 25 minus 37 divided by what? 25i. So in this, in this manner, we are written in standard form. And what's the real part? The real part now is this. So that's the real part of the complex number. Real part is 16 divided by 25. And the imaginary part of the complex number, im, is 37 divided by what? 25. Let us take, one or two more examples. So here we have 3 minus 5i divided by 5 minus 3i. So the procedure is the same. Multiply numerator and denominator by the what? Complex conjugate of the denominator. So let's proceed. We have 3 minus 5i over 5 minus 3i times. The denominator here is 5 minus 3i. So the complex conjugate of 5 minus 3i is what? 5 plus 3i. Divide by the same complex conjugate, 5 plus what? 3i. We multiply out. So this means 3 minus 5i multiplied by 5 plus 3i divide by 5 minus 3i times 5 plus what? 3i. So 3 times 5 is 15. 3 times 3i is plus 9i. Minus 5i times 5 is minus 25i. And minus 5i times 3i is minus 15i squared. Divide by 5 times 5 is 25. 5 times 3i is plus 15i. Minus 3i times 5 is minus 15i again. And then minus 3i times 3i is minus 9i squared. So we have 15. 9i minus 25i is minus 16i. Minus 15 into I squared is minus 1. Divide by 25. 15i minus 15i is 0. Minus 9. I squared is again is minus 1. Equal 15 minus 16i. Minus 15 times minus 1 is plus 15. Divide by 25. Minus 9 times minus 1 is plus 9. So this is equal to 15 plus 15 is 30. Divide by 25 plus 9 is what? Is 34 minus 16i. So we can write this again in standard form as what? 30 over 34 minus 16 over 34 I. So that the imaginary part, this is 9 plus, okay. The real part is 30 over 34, and the imaginary part is 16 minus 16 over 34. Of course, we can break this further down, to its lowest term. Argand plane. The plane whose points represent complex numbers is called the complex plane. It is also called the Gauss plane. It is also called the Argand plane. So just like we, could represent real numbers, on our x and y coordinate system, we can also represent complex numbers in what we call the Argand plane. So the Argand plane is a plane that looks just like this. Like this. So your x-axis here, the positive x-axis here becomes the positive what? Real axis of the complex number z. The negative x-axis we know becomes the negative real axis of the complex number z. This other side becomes the positive what? Imaginary part of the complex number z, and the down part becomes the negative imaginary part of the complex number z. So, and here is the origin 0, 0. So we call this plane the Argand plane. And on this Argand plane, we can represent any and every complex number. So on the real plane, this is your real x-axis. This is your positive real x-axis. This is a negative real x-axis. This is your positive y-axis. This is your negative y-axis. On the Argand plane, this is your positive real axis, negative real axis, positive imaginary axis, and the negative what? Imaginary axis. So we shall represent some complex numbers here and see what happens. Let us look at z1 equal to, say, 2 plus 3i. Let us see how to locate. So this complex number given, z1 equal to 2 plus 3i. This complex number has imaginary real part 2, positive real part 2. So on our Argand plane, the positive real axis is this way. So on that real axis we have 2. So 2, let us just say 2 is somewhere here. And in the imaginary part we have 3. And we have plus 3. So imaginary part is positive. We are going along this other way. So plus 3 is somewhere here. So we now check, where do these 2 points meet? So plus 2. So 2 is here, and then 3 is here. They meet somewhere there. So at that point, z1 is written as a complex number. We can write 2, 3. Or we can write z1 equal to 2 plus 3i. So we'll now trace from that point to the origin, the straight line. So that's a complex number, z1 equal to 2 plus 3i. Now take note of this notation. We can also write z1 as 2, 3 as what we call an ordered pair. This pair is called an ordered pair in the sense that the first value in this pair must be the real part of the complex number, and the second value in this pair must be the imaginary part of the complex number. That is to say, if you write this as 3, 2, then you are wrong, because 3, 2 would mean that the complex number z has real part 3 and imaginary part 2, and that is not correct. So this complex number z has been located on the Argand plane, the Gauss plane, or the complex plane. So this is z1. Let's look at another complex number, for example, z2 equals to minus 3 plus 2i. Let us see. The real part is negative, so real part is negative. We come this way. So negative 3, somewhere here. Let us call that point negative 3. The imaginary part is positive, so we are still going up, plus 2. So plus 2 somewhere here. Let's call that point plus 2. So we now trace a complex number. So negative 3 plus 2, they meet somewhere here. So from that point to the origin, so this point here, z, so z2, real part is minus 3, imaginary part is what? 2. That's a complex number, z2. We can trace another complex number, z3, equal to 4 plus, say 4 minus 3i if you want. Now this complex number has real part to be positive, so real part is positive. We are here, 4 is somewhere here. Let's call that point 4. And the imaginary part is negative, so we are now down here. Minus 3 is somewhere here, call it minus 3. So we now trace to see where they meet. So minus 3 and 4 meet somewhere here. So we now trace from the origin. So that point z3, ordered pair, real part is 4, imaginary part is negative 3. That's a complex number. And lastly, let us trace one more. Z4 is equal to, say, minus 6 minus 4i. So the real part is negative. So negative real part is here. Minus 6 is somewhere here. Minus 6. The imaginary part is minus 4. It's negative. It's down here again. Somewhere here. Minus 4. So we trace to see where they meet. Of course, they meet at this point. We now draw from the origin to that point. That is Z4. Real part is minus 6. The imaginary part is what? Minus 4. It is important to learn how to locate points on the Argand, plane or the Gauss plane, because later on, when we shall be dealing with argument of a complex number, it will be very important to know how to locate your complex numbers on this plane. And of course, this plane is divided into what they call 4 quadrants. The first quadrant, second quadrant, third quadrant, and the fourth quadrant. We'll make comment on this, a while later. The last thing we'll be looking at, in this video is the modulus of complex number, or modulus of a complex number. So definition. Given a complex number, z equal a plus ib. The modulus of z is defined as, we put z, between two straight bars. So this means modulus of z is equal to the square root of a squared plus b squared. Now you see that the modulus of z simply means you take the square root of a here is the real part, you square it, b here is the imaginary part, we also square it and take their sum. Sometimes you can still write this as r to mean the modulus. Now, geometrically speaking, what does it really mean? Now, let us go back to our Argand diagram and look at the complex number z equal to a plus ib. So this complex number has real parts to be positive, same as imaginary part, so it must be somewhere here. So that's a complex number, z, a, b. What we really mean by the modulus of a complex number here is this. When you evaluate this, when you calculate what you're seeing here, what we're actually checking is the length of the complex number from the origin to the point where z is. So this point here, z bar or r, is what we refer to as what? The modulus of the complex number. So we are referring to the length or the magnitude of the complex number z equal to a plus ib. Let us take one or two quick examples to illustrate how we make use of the formula. Example: find the modulus of the complex number z1 equal to 4 plus 2i. So here, the real part is 4 and the imaginary part is 2. So the modulus of the complex number z1 will denote as z1 between two straight bars. Sometimes we use r to represent the modulus. Is equal to the square root of the real part is 4, so 4 squared, plus the imaginary part is 2 squared. And that becomes the square root of 16 plus 4. And that is equal to the square root of what? 20. Now from our knowledge of sorts, we can write this as the square root of what? 4 times 5. And that gives us 2 root 5. So what this simply means is that on our Argand diagram, or on our Argand plane if you want, if we locate this complex number, z1 equal to 4 plus 2i, the real part is 4, so 4 is somewhere here, call that point 4. The imaginary part is 2 is somewhere here, and the complex number is 2. Complex number meets here. So this is z, real part is 4, and then 4,2. What we are saying here is that the distance, the length of this complex number, the distance from the origin to this point is 2 root 5. That's what we mean by the modulus of a complex number. Let us take two more examples, or one. Example 2. Find the modulus of the complex number z2 equal to 2 root 6 plus 5i. So here, the real part is 2 root 6, and the imaginary part is what? Is 5. So the modulus z2 of the complex number given to us, modulus or length if you want, is equal to the square root of the real part, which is 2 root 6, so 2 root 6 all squared, plus imaginary part is 5 plus 5 what? Squared, equal to the square root of, now 2 root 6 all squared, we have to be careful with it, 2 squared is 4 times the square root of 6 all squared is 6. Since 2 will cancel the square root. Plus the square root of 5 is 25. This is equal to the square root of 4 times 6 is 24 plus 25. That gives us what? So 24 plus 25 gives us the square root of 49. And what is square root of 49? 7. So once again, this means that if you locate this complex number on the Argand plane, then the distance or the length of the complex number from the origin will be what? 7 units. The last example. So if we want to find the modulus of the complex number, say z3 now equal to say 1 over 2 plus say 1 over 2i. So in this case, the real part is 1 over 2 and the imaginary part is also 1 over 2. So the modulus of the complex number z3 is equal to the square root of 1 over 2 squared plus 1 over 2 squared. That gives us a square root of 1 over 4 plus 1 over 4. And of course, 1 over 4 plus 1 over 4, 1/4 plus 1/4 is equal to a half. We can write this as 1 over the square root of what? 2. You can stop here if you want, or go ahead and rationalize. If you rationalize what 1 over root 2, you get root 2 over 2 units. So once again, it means that if we locate this complex number on our Argand plane, the Gauss plane or the complex plane, then the distance or the length of the complex number from the origin 0, 0 to wherever it is will be what? The square root of 2 over 2 units. Please do not fail to leave a comment and a like on this video. Thank you and bye-bye.